Welcome to the section of multivariate analysis. Let's start with the introduction. Multivariate analysis is concerned with analyzing and understanding data in high dimensions. It is a set of techniques that used for analyzing or analysis of data sets that contain more than one variable. And the techniques are especially valuable when working with correlated variables. The techniques provide an empirical method for information extraction, regression, or classification. Some of these techniques have been developed quite recently because they require the computational capacity of modern computers. There are two types of multivariate technique is there, that is dependent techniques and interdependence technique. Dependence technique is a variable or a set of variables is identified as the dependent variable to be predicted or explained by other variables known as independent variables. And interdependence technique, that means it involves the simultaneous analysis of all variables in the set without distinction between dependent and independent variables. And here you can see the classification of multivariate methods. That's showing a flowchart here. That is, multivariate method are two types: dependence method and interdependence method. So in dependence method, there is dependent and independent variables is there. That is, we can divide the dependence method into two, that is one dependent variable and several dependent variables. For example, for one dependent variables are multiple regression, discriminant analysis, logistic regression. These are the some examples for one dependent variables. And analysis of variance, that is ANCOVA, and canonical correlation techniques are the examples of several dependent variables. And another technique is interdependence method. In this method, we are using the statistical technique like factor analysis, cluster analysis, and MDS. MDS means multi-dimensional scaling. So these are considering as the interdependence method. In this section, and here no distinction between dependent variable and independent variable. And in this section, I will going to explain about the multivariate regression and logistic regression. Linear regression of the dependent measurable variable, that is considered as y, on several independent variables x1, x2, etc. xp is studied to find out whether the independent variables are related to y or not, and if related, which all of them are significantly related, indicating the order of their importance. Also, it will help us in the prediction of the value of the dependent variable based on the significantly contributing independent variables. It also indicates the error observed in the predictions. So that is, in multiple linear regression, we are predicting the dependent variable based on the several independent variables. For example, prediction of birth weight of babies based on mother's nutritional status, age, weight, height, and gestation period, and an order of the birth of the baby. Another example, the prediction of blood pressure based on patient's age, sex, occupational status, income, weight, and marital status. Based on these risk factors, you can predict the patient's blood pressure, or you can predict the weight of the babies, birth weight of the babies. The model of the multiple linear regression is y equal to beta naught plus beta 1 x1 plus beta 2 x2 plus etc. plus beta p xp plus epsilon, where y is the dependent variable, x1, x2, etc. xp are the independent variable, p number of independent variables, and beta naught is constant, b1, beta 1, beta 2, etc. beta p are the regression coefficients, and epsilon is the error terms. Next is the assumption of the techniques. There must be a linear relationship between the outcome variable and the independent variable. That is the first assumption, that is linear relationship. How we can identify the linear relationship? By the graphical method of scatter plots. So within this scatter plot, you can see whether the variables relation follow a linear or curvilinear relationship. Another assumption is multivariate normality. Multiple regression assumes that the residuals are normally distributed. Residual means the error terms, that is, error means the difference between the observed value and the predicted value, that is considered as the error term. That error should be follow a normal distribution. Another assumption is now multicollinearity. Multiple regression assumes that the independent variables are not highly correlated with each other. This assumption is tested using the statistical technique, that is variance inflation factor values. And another one assumption is homoscedasticity. This assumption states that the variance of error terms are similar across the values of the independent variable. And this can be checked by the scatter plot diagram that you can draw based on the standardized residual versus predicted values, can show whether points are equally distributed across all values of the independent variables. Here you can see one example of weight. Here the variables are weight, height and age of 12 nutritionally deficit children. So here 12 number of children is there, corresponding their weight, height, weight in kg, height in centimeter and age measured in months. Here the question is, can we predict the weight of the children by their height and age? Let's start with the univariate regression. Here the first one is univariate regression of y on x1 alone. The linear univariate regression model is y equal to a plus b1 x1, and here we get the b1 equal to 0.107 and a equal to 0.6252. I think in the last in the regression class you already learned about the linear regression. What is A? A is a constant and B is the B is the regression coefficient or slope. So here you can see the regression coefficients equal to 0.1072 implies that for every 1 unit increase in the independent variable, there is an increase of 0.1072 units in the dependent variable on average. That is, the regression coefficient means 1 unit change in the independent variable corresponding how many variation are taken on the dependent variable. The regression equation of weight on height is y equal to 0.6202 plus 0.1072 x1. So here y is the weight of the children and x1 is the height of the children. So using one, here we are taking one independent variable, that is height is the independent variable. Using that height independent variable, we are estimating or we are predicting the weight of the children using this equation. The correlation coefficient between y and x1 is 0.8143. Here the correlation value is 0.8143, means which is a high positive degree of correlation. If there is no correlation between y and x1, we are not going to the regression analysis. And here one times we will get the coefficient of determination, that is considered as the square of the correlation value. So that is square of the 0.8143, which will get 66.31%. That is considered as the coefficient of determination. That implies that height alone explains about 66% of the total variation in the weight of the children. Understood? That is, the 66% of variation on the weight is explained by the variable height alone. Using the regression equation, we can predict the weight of a children for a given height. For example, the height and weight of the first children in our sample are 57 cm and 6.4 kg respectively, as against the observed weight of 6.4 kg of this child. Our regression equation based on the height alone predicts the weight as that is we can put these values on the regression equation. Weight, that is y equal to 0.6202 plus 0.1072 into x1. So here we are taking the x1 as 57 centimeter. Put the value of x1 in this equation, we will get the weight of the predicted weight of the children, that is 6.73 kg. So actually within the observed data you can see the children's actual weight is 6.4 kg. Here we get the predicted weight is 6.73 kg. So there is an error there. So the error is 6.4, observed value minus the predicted value will get 0.33 kg. That is the error this difference is considered as the error time. The second univariate linear regression of y on x2 alone. The linear univariate regression model is y equal to a plus b2 x2. Why it's called univariate regression? Here we are taking only one independent variable for predicting a dependent variable. So this type of model is considered as univariate regression. If we are considering more than one independent variable, that we are considering as the multiple linear regression. And here you can see the linear univariate regression model is y equal to a plus b2 x2, and here we get the constants. B2 is the regression coefficient, will get 0.3643, and the intercept is considered as a, that is 3.0632. That is the regression coefficient equal to 0.3643 implies that for every 1 month increase in the age, there is on average an increase of 365 gram in the weight of the children studied. That is, here the x2 is, what is x2? x2 is considered as the independent variable, and in this example the x2 is the age of the child. That age of the child we are estimated in months. So 1 unit, that 1 month increase in the age corresponding 0.3643 kg of weight were increased. The regression equation of weight on age is y equal to 3.0632 plus 0.3643 S2. The correlation coefficient between y and S2, that is weight and age, is we will get the R2 equal to 0.7699, that is positive high correlation, moderate high correlation, and corresponding coefficient of determination that we consider as the square of the correlation coefficient will get 59.27%. It implies that the height alone explains about 59% of the total variation in the weight of children. For the first child in our sample, the regression equation based on age predicts weight as 3. That is, we can apply this age of the children to the equation. The equation is 3.0632 plus 0.3643 into the age of the first child, that is 8 months, into 8. We will get 5.98 kg is the predicted weight as against 6.4 kg observed. That is the actual weight of the child. The predicted weight is 5.98 kg. So there is an error there. So the error become 6.4 minus 5.98 will get 0.42 kg. Next we are come to the multiple linear regression model, and that is y equal to a plus b1 x1 plus b2 x2, where the constant a equal to 0.6563 and the regression coefficient b1 equal to 0.0722 and b2 is the 0.2050. The final multivariate regression model is y equal to 0.6563 plus 0.0722 x1 plus 0.20 x2, and corresponding regression coefficient of determination will get 78%. So that is both height and age together explain 78% of the total variation in weight. Now let us try to predict the weight based on two predictors, namely height and age. For the first child, predicted weight would be 0.6563 plus 0.722 into x1. What is x1? x1 is the height of the first child, that is 57, plus 0.2050 into x2. x2 is the age of the first child. So we are applying the age of the first child as 8. So we will get 6.41 kg. That is the predicted weight of the child, 6.41 kg. The resulting error in the prediction now is 6.4. That is the actual weight of the child minus the predicted weight 6.41 will get 0.01 kg, which is an improvement on the prediction based on height and age alone. And here you can see if we are including the two predicted variable to the model, then that situation the error will reduce. And in this table you can see the model. Here we can see the three model. The model 1 including one independent variable that is considered as height. Corresponding regression coefficient will get 0.1072 and the coefficient of determination 66.3%. In the model 2 we are including the age as the independent variable. So corresponding regression coefficient is 0.3643. And correlation coefficient of determination will get 52.80%. And the third model we are including both the independent variable height and age. In that situation the regression coefficient corresponding for height is 0.0722 and for weight is age is 0.2050. Corresponding coefficient of determination will get 78%. Taking the model 3 as the final, the regression coefficient of 0.0722 associated with height implies that on the average there is an increase of 72 gram in the weight, adjusting for the influence of age on weight. As done in the given example, any number of variables can be considered in multivariate regression analysis. The variation can be explained on the basis of each of the variable alone and in various combinations, and their individual contributions can be investigated for statistical significance to enable us to have better prediction of the dependent variable. Next one is the multivariable logistic regression. Multivariable logistic regression is the statistical technique used when we wish to estimate the probability of dichotomous outcome, such as the presence or absence of a disease or of death. The probability of outcome is the dependent variable and the various factors that influence it are the independent variables, sometimes termed as risk factors. In the multiple linear regression, we are considered as the dependent variable as a continuous measurement. But in the case of logistic regression, we are considering the dependent variable should be a dichotomous or binary outcome variables. Mainly in this section, we are focusing on what are the independent factors for predicting a disease condition. Some applications are that is prediction of outcome, for example improved or not improved in a clinical trial, to compare the effect of new drug with that of standard drug in patients of disease based on patient's age, weight, BP, nutritional status, duration of the disease, diet, habits like smoking, alcohol use, etc. Using these factors, we can predict whether the patient improved or not improved. Another example, prediction of prognosis, whether the patient would be cured or not, based on his or her age, sex, weight, severity of the disease, duration of the disease, cholesterol value, BP, sugar level, type of treatment received, etc. Here you can see the simple linear regression model, that is y equal to beta naught plus beta 1x plus epsilon, where we are trying to predict a continuous dependent variable y from a continuous independent variable x. And this model can be extended to multiple linear regression model, that is y equal to beta naught plus beta 1x1 plus beta 2x2 plus etc plus beta pxp plus epsilon. Here we are trying to predict a continuous dependent variable y from a several continuous dependent variable x1, x2, etc. Here we attempt to predict the outcome of binary response variable y from a several independent variables x1, x2, etc. And the model logistic regression model equal to log of p divided by 1 minus p equal to beta naught plus beta 1 x1 plus etc plus beta p xp. And that also we can rewrite in the form of p equal to 1 divided by 1 plus exponential of beta naught plus beta 1 x1 plus etc plus beta p xp, where beta naught, beta 1, beta etc beta p are the logistic regression coefficient, and log of p divided by 1 minus p is called log odds or logit of the event. For example, in a cohort study of 12-year incidence of CHD in 2,187 men and 2,669 women aged 30 to 62 and found free of coronary disease at first examination. 7 different factors measured at the initial exam were studied for their effects on the 12-year incidence of CHD. The variables are: x1 considers age in years, x2 serum cholesterol mg per dl, x3 is the systolic blood pressure in mmHg, x4 relative weight, x5 hemoglobin, and x6 is the cigarettes per day. So x6 is considered as a categorical variable that divided into 4 categories. That is, category is coded as 0 representing never use of cigarettes, and 1 representing less than 1 pack, 2 representing 1 pack per day, and 3 representing more than 1 pack cigarettes per day. From the software outputs, we will get the parameters corresponding for the each variable. That is, here x0 is considered as the intercept, and x1 age corresponding regression coefficient will get 0.1216, corresponding for cholesterol 0.0070, corresponding for SBP 0.0068, for relative weight 0.0257, for hemoglobin minus 0.001, for cigarettes 0.4223. You don't bothered about this regression coefficient, how we'll get the regression coefficient. If we have data, we can apply this data on the software, and from the software we will estimate the output, and from the output we can identify the regression coefficient for the each variables. Now the probability of developing CHD within 12 years of an initial exam for a man aged 40 to 49 years is thus represented by, that is, we can apply that regression coefficient to the equation, to the logistic regression model. What is the model? That is p equal to 1 divided by 1 plus exponential of beta naught plus beta 1 x1 plus etc plus beta p xp. So corresponding beta naught, beta 1, beta 2 etc, these are the regression coefficient. Corresponding values we can put in the given equation. That is, p equal to 1 divided by 1 plus exponential of minus 13.2570, that is the constant beta naught, plus beta 1.1216 into x1 plus etc plus beta 6.4223 into x6. This is the logistic regression model. When we know the value of the independent variable, we can put that value on this equation and corresponding patient's CHD probability will predict. Here you can see one example. A man with the following characteristics, that is age 45, cholesterol level 210, SBP 130, relative weight of the corresponding patient is 100, hemoglobin was 120, cigarettes smoking is coded as 0, that is never smoked. That person is never smoked. So we can apply these values to the equation logistic regression model. Then we get P equal to, that is 1 divided by 1 plus exponential of beta naught plus beta 1 x1. x1 we can put the value of x1 is age 45 plus 0.0070 into x2. x2 is considered the cholesterol level. The value of the cholesterol level we can put here, and etc. Final we get point, the p will get 0.048. What is the interpretation? For every 1,000 men with the preceding characteristics, one expects 48 to develop CHD within 12 years. Another example, a man with the following characteristics, that is age 46, cholesterol level 210, SBP 130, relative weight 100, hemoglobin 120, and cigarette smoking is 3. That is coded as 3. 3 means what? More than 1 pack cigarettes per day. Therefore, the probability of the CHD for the corresponding patient will get 0.1526. That is for every 1,000 men with the preceding characteristics, one expects 152 to develop CHD within the 12 years. That is, the 12-year risk of disease for the smoker related to the risk for the non-smoker is 3.16. That is, this is the ratio of the probability of developing CHD to the patients that received more than 1 cigarette per day to non-smokers. Smoking 1 or more packs of cigarettes per day is estimated to increase the odds of disease related to non-smoking by the factor exponential of beta. Beta is considered as the corresponding regression coefficient of the cigarettes use. That is, here we get 0.4223 into the code of the more than 1 cigarettes per day. So we will get the value is 3.55, which is considered as the odds ratio. So what is the interpretation of odds ratio? Here the odds ratio is 3.55. That means as compared to non-smokers, the person who have smoked 1 or more packs of cigarettes per day have 3.55 times high risk for developing CHD. Next one is analysis of covariance, that is ANCOVA. Let's start with the introduction. In ANCOVA, the main variable under study is a continuous variable and the blocking factors are discrete variable with categories. If there is another continuous variable that is called the covariance or concomitant variable, which may affect the main variable, then for a valid comparison of the main variable between two or more than two groups, the effect of the covariate should be taken into consideration. This will increase the precision of the comparison. This analysis is called analysis of covariance or ANCOVA. In any study involving a single quantitative variable, say systolic blood pressure, design of experiments may fall into one of the three categories. The first one is studying the difference in average values of the dependent quantitative variable between a number of categories of one or more qualitative independent variables. For example, studying the differences in average blood pressure between various ethnic groups and between sexes. The analysis of variance is the statistical technique that applied for this purpose. This analysis helps us in sorting out the variation due to the ethnic group and sex, and thus we can reduce the error variation and increase the precision of the estimate. So, in conclusion, the regarding of hypothesis of no difference in blood pressure between sexes and between ethnic groups will be more valid in such analysis. The second category is studying the possible changes in the dependent variable which may accompany changes in quantitative independent variables. For example, studying the possible changes in systolic blood pressure values which may accompany changes in the age of the subjects. So, in that situation, we are applying the correlation and regression analysis technique. The third category is studying the differences in average values of the dependent quantitative variable between a number of categories of a qualitative variable. When it is known that another quantitative variable may influence the quantitative variable linearly. For example, we are interested in studying the differences in average systolic BP values of two groups of head patients after giving two different drugs, taking into consideration the information on BP values before and after giving the drugs. So, since it is known that the BP values after giving the drugs are influenced by the values before giving the drugs, isn't it? So that is comparatively higher values may be recorded for those with higher initial values, and lower final BP values may be recorded for those with lower initial values, showing a good correlation between initial and final BP values. So if this fact is not taken into consideration, the conclusion arrived at only from the final values would not be valid. The most appropriate analysis to be applied for such a design is called an analysis of covariance, that is ANCOVA. The quantitative independent variable in ANCOVA is called a covariate or concomitant variable. Other purposes of ANCOVA: apart from increasing the precision of estimate, which is the most common use of covariance analysis, it can successfully be applied for the following purpose also because of the inherent nature of the analysis of covariance. First of all, to adjust the sources of bias in observational studies, that is, we can adjust the effect of the bias in observational studies. For example, in comparing BP values of two groups of patients, if there are age differences between two groups, and also if it is known that the BP value and age are linearly related. So ANCOVA helps us to adjust the possible bias due to age. So this bias could have been avoided by randomly allocating the patients in two groups. If that was not possible at the design stage due to some reasons, ANCOVA can be removed this bias at the analysis stage. The second purpose is to remove the effect of disturbing variables in observational studies. That is, in observational studies where naturally occurring groups like ethnic groups or sexes are studied, to have a valid comparison of the averages of the study variable, say weight, between these groups, taking into consideration the fact that age of the subject can affect the weight values. Through age is not a concern of the study, ANCOVA can be applied to remove the effect of this disturbing variable, age. The third purpose is to study the regression in multiple classifications. For example, in studying the relationship between age and cholesterol in three different ethnic groups, ANCOVA can be applied to examine whether the relationship is the same or different in the different ethnic groups. Here you can see the multiple regression process, and in multiple regression the dependent variable y should be a continuous form, and continuous independent variables like x1, x2, etc. xp are taken. The continuous independent variables x1, x2, etc. xp are quite often measured and observed. In the case of analysis of variance, the dependent variable y should be a continuous form, and the categorical independent variables that we are taking, that is like a, b, c, different categories are there. The categorical independent variables a, b, c are set to specific values or levels. And in ANCOVA, we can see the dependent variable is y, that should be continuous data, and categorical independent variables are there, and also continuous independent variables also there, that is considered as the covariate. In ANCOVA, we need to adjust the effect of the covariate variables on dependent variable. And here you can see the ANCOVA model, that is y equal to mu plus alpha I plus beta j plus etc. Plus alpha plus gamma I x1, gamma 1 x1 plus gamma 2 x2 plus etc. plus epsilon, where gamma 1 x1 plus gamma 2 x2 plus etc. is considered as the covariate effects. And this is the table of the ANCOVA model, and here you can see the sources including the covariate effects, main effects, interaction effects, and error total, and sum of squares corresponding for each sources are given, and degrees of freedom we can find. Based on this sum of squares and degrees of freedom, we can estimate the F statistic. Based on the F statistic, we are deciding whether the null hypothesis is accepted or rejected. Assumptions of the ANCOVA. Before initiating a detailed analysis of the group effects, that is comparing the means of the study variables between various groups after adjusting for the influence of the covariate, certain important assumptions that have been made for covariance model have to be tested. The assumptions are: for each independent variable, the relationship between the dependent variable y and the covariate has a linear relationship. The lines expressing these linear relationship are parallel. The covariate is independent of the treatment effects. That is, the covariant and independent variables are independent. For example, here we are taking the dependent variable y as weight gain, and categorical independent variables are considered as the factor. That is, here we are taking the sources of protein as the independent categorical variable. That sources of protein are divided into three categories: beef, cereal, and pork. And the continuous independent variable, that is considered as the covariate. The covariate variable are initial weight of the animal. And this is the data. Here you can see the three variable: weight gain, initial weight, and source. And in this ANCOVA table, we are comparing the mean weight gain between the different sources of protein groups. So here the p-value is 0.322, that is, which is greater than 0.05, that we can conclude that there is no significant difference in the mean weight gain between the different sources of protein groups. Only using this ANCOVA table, we can conclude that there is an independent relation between sources of protein and weight gain. So we need to take the conclusion based on the ANCOVA table. When we take the ANCOVA table, if there are any correlation between weight gain and initial weight, in that situation we are applying ANCOVA. So here I am not given the correlation between weight gain and initial weight, but actually using this data there is a high correlation between initial weight and weight gain. And this is the SPSS output of the ANCOVA table. Here you can see the sources, corrected mode, intercept, source, initial weight, source interaction between source and initial weight, and error times. So in this you can see the p-value in the last column corresponding for the sources are significant. That is, there was a significant difference in mean weight gain, that is p-value is 0.027 between the sources whilst adjusting for initial weight. The dependent variable is adjusted so that the covariate takes on its average value for each case. The effect of the factor is determined using the adjusted value of the dependent variable. That is, even after adjusting the effects of initial weight, there is a dependent relation between weight gain and sources of protein. Thank you.